So here we have a case of a pulley system where we have one string that's horizontal and one string that's vertical. So let's go through this question. Two particles A and B of masses 0.4 and 0.8 kilograms respectively. So A is 0.4 kilograms and B is 0.8 kilograms. Connected by a light inextensible string, which means the tension in the string is the same all the way through. So the tension on the pulley is the two next to the pulley. The tension on block A is the one on the left. The tension that's affecting block B is the one at the bottom. Particle A lies on a rough horizontal table 4.5 meters from a smooth pulley, which is fixed. So this distance here is 4.5 meters. The string passes over the pulley and hangs freely with the string taut 0.5 meter above the ground. So if we have the ground here, this is going to be 0.5 meters. A frictional force of magnitude 0.08 g opposes the motion of the particle. So we have a frictional force here of 0.08 g. So let's also include our weight force and our normal reaction force. So our weight is going to be 0.4 g, because it's 0.4 kilograms, and our reaction force will be equal to that, because if it was not, then the particle would be, the mass would be sinking into the table. So the system is released from rest, and you can see that we're going to accelerate, and you can see I'm going to do another curved arrow here. We're going to accelerate in this direction. So first thing we want to do is find the acceleration of the system. Now, the first thing I would do is consider the system as a whole. So altogether, if we consider the system as a whole, we have a mass of 1.2 kilograms. And if we think about starting here and finishing here, going from A to B, then we have a resultant force this way of 0.08 g. All of the tensions in the string cancel each other out. And then we have a weight down here of 0.8 g, so we have a force this way of 0.8 g. And we're clearly accelerating towards B. So if I resolve my forces in the system in this direction, I get 0.8 g. Take away 0.08 g. It's going to equal 1.2 a. So I get 0.72 g equals 1.2 a. 0.72 divided by 1.2, so 7.2 divided by 12, and 12 sixes are 72. So we get 0.6 g as our acceleration. I'm going to leave it as 0.6 g because I know that g is 9.8. And often the question might ask you to leave your answer in terms of g, and that's okay. So that's my acceleration, 0.6 g. Find the time taken for B to reach the ground. This is where we need to start using Suvat equations. So you can see that the distance B is from the ground is 0.5 meters. And we can use Suvat because we have a constant acceleration here. So S is 0.5 meters. We are released from rest, so our initial velocity is 0. We don't know what our final velocity is. We know our acceleration is 0.6 g meters per second squared. And the time is what we're trying to calculate, the time taken. So let's call that, I'll call that capital T. So we want to use S equals ut plus half at squared. And in this example, u is 0. So we just use S is half AT squared. So 0.5 is half A, so that's 0.3G T squared. So we have a half is 0.3G, so we can divide both sides by 0.3, and then divide both sides by G as well. So we get 5/3. Let me rewrite that. We get 5/3G is equal to T squared. So our time taken is the square root of 5/3G, or 5/3G is 5/3 times 9.8. And then square root that to get our answer. We get 5√3/21 on the calculator, or 0.41 seconds to two significant figures, which is a useful measurement to do because we had our gravitational constant as 9.8, which is to two significant figures. So the total time to take it to reach the ground, 0.41 seconds. Now, the total distance travelled by A before it comes to rest. Now that's an interesting question, because if you think about it, in the first part of this motion, as B approaches the ground, B is going to travel 0.5 meters. That means A is also going to go this way 0.5 meters. But once B hits the ground, the string will no longer be taut, which means we're going to lose our tension in the string entirely. So the first thing I'm going to do is I'm going to calculate the velocity that A will be traveling at after that first half a meter. The reason I want to do that is so that I have a little bit more information about the motion of A. Therefore, I can use that information to calculate how much further A is going to travel before it stops. All right, so let's think about that then. So this time, we don't need to, we can use the same information, but we don't need to know what our time is anymore. We want to know what our final velocity is. So we should recognize from this that we can use v squared is u squared plus 2as. So our v squared is equal to 0 squared plus 2as. So 2a is 1.2g and s is 0.5. So it is the same as our acceleration, 0.6g. So our final velocity is the square root of 0.6g. So the square root of 0.6 multiplied by 9.8, and it gets us 7√3/5, which is 2.4 meters per second. Now I'm going to use the more accurate version because this is only to two significant figures. So I'll store that on my calculator so I know exactly what that value is. Okay. So now I'm going to think about after B hits the floor. After B hits the floor, this model here is no longer valid. All right, we can't use it anymore because the tension in our string is completely gone. So we don't have a system of forces anymore. We just need to think about the particle A. So the particle A, 0.4 kilograms, will still be traveling to the right, but there will be no tension pulling it that way. There will just be a frictional force of 0.08 g. And yeah, we still have the 0.4 g here and here as our reaction force, but that's not going to affect our horizontal motion at all. So let me just get rid of this because this time, now we don't have tension, we also don't have an acceleration that is the same as it was before. This time our acceleration will be a deceleration, so it'll be an acceleration in this direction. And we need to think, what we need to do is we need to recalculate that acceleration first before we can continue with the question. So our new acceleration, based on this new initial condition here, if we resolve our forces in this direction, because that's the way we're accelerating, we have 0.08 g is equal to our mass, which is 0.4, times by our acceleration. So if we can then rearrange this, we can divide everything by 0.4, and we get our acceleration is 1.96 meters per second squared to the left. All right. I'm going to continue to use that direction as positive, but I'm also now going to include the fact that when we start, we're moving in this direction at a velocity of 2.4 meters per second. That's going to be important. The direction is important there. So we want to find out how far A is going to travel. We know our initial velocity is 2.4 meters per second. And this is the two significant figures. And remember, it's in the other direction. We've taken left to be positive, so this is minus 2.4 meters per second. We know our final velocity is going to be 0 because we want the distance before it comes to rest. And our acceleration now is going to be 1.96 meters per second squared to the left. So it's a positive value because we've taken left to be positive. And we don't know the time taken, and we're not really interested in the time taken, so I'm just going to ignore that. Okay. So again, you can see here we're going to be using v squared equals u squared plus 2as. And our v is 0. Our u squared is going to be the answer we got before squared. So it's a negative number squared, which is 5.88 in this case. So I've used my exact value. I haven't used my 2.4 because that was the two significant figures. And then plus 2a, which is 1.96. And then s, which is x. Okay, so you see, I'm going to end up with a negative distance there, which makes a lot of sense because this thing is traveling in this direction, and when it comes to a stop, use a different color. When it comes to a stop, it will have traveled in that direction and not to the left, and that's in our negative direction. So we should have a negative value for x, and that makes sense. So what we have here is 2 times 1.96 to get us 3.92 x, and that's equal to negative 5.88. So if we do that negative 5.88 divided by our 3.92, we get a value for x to be negative 1.5. So you can see what we've done here is we've travelled another 1.5 meters in this direction. So we're almost there. The total distance travelled by A before it comes to rest, well, we've got to remember that we initially travelled half a meter. Okay, so the total distance travelled is going to travel 0.5 meters while we have tension in the string. And then we're going to travel another 1.5 meters in this direction after the string becomes loose and there's no longer any force acting on the particle. So it's going to be 0.5 plus the 1.5 meters